This unit, we're going to be looking at gases and primarily what's called gas laws and the properties of gases and their behaviors. And of course, we have so many different gases that exist in our world. The most abundant in our atmosphere, of course, is nitrogen and oxygen, but we can also look at noble gases like krypton, carbon dioxide, which of course is definitely an important gas, noble gas like argon, xenon, and so many more, methane that we burn in our furnace. So these are all gases, and so this unit's going to look at the properties of these gases and the behaviors of these gases.
Okay, so to get started, we're going to be looking here in the book, and you can definitely follow along. So we're going to look at pages 212 through 214 and do some problems on 222. And this introductory video on gases will be focusing on some simple properties of pressure, volume, temperature, and amount of substance. And these are properties that can be measured or calculated. So we're going to get started.
Okay, so let's just look at some of the properties here of gases. And here I have a gas filled with some helium. I'll add some neon, argon, krypton, and xenon. So a mixture of different gases, just to look at the properties of gases and characteristics of gases. So the first is that gases can expand indefinitely and uniformly. So if I give the gases a bigger container, they're going to continue to expand. So they're going to expand to the size of the container that we put them in. Gases, and that kind of goes with the second, and that is gases have no definite shape or volume. Again, just depending on the size of the container I put that gas in, that will be a specific volume. And gases can be highly compressed, so we can kind of really get those gas molecules pushed really close together. And if we compress them, we can turn them into a liquid and in some cases a solid. So we can compress them to a different state of matter. And then number four is gases are of lower densities than liquids and solids. So you can see sort of this modeling, gases spread out. They can occupy a container, but most, as you're going to see here with the gases, they don't take up as much, or there's not as many gases in the same container as you would see with solids or liquids because they do spread out so much. And then the fifth is most non-reactive gases mix uniformly. They mix uniformly because they're so spread out and their intermolecular forces really don't affect each other. So they really just exist, and we can say they exist as a homogeneous solution. That's kind of what's unique about gases.
So now let's get started with the properties of gases, those that are associated with gases. And we're going to start here with pressure. And with pressure, we are looking at the gas molecules, and pressure is actually force divided by area. So it's the amount of force in a certain amount of area that these gas molecules or gas atoms will exert on each other. And what I like to look at in terms of modeling is how many collisions. So those increase of collisions is an increase of pressure, and that's collisions with each other or collision with the wall container. How we measure that pressure? Well, there's different instruments that have been used, and one of the older of instruments is called a manometer, and I like it because it helps explain one of our gas law units, which is the millimeters of mercury for pressure. And what we see with that is when you have mercury in a dish, which mercury, of course, is a liquid, and atmospheric pressure, if that atmospheric pressure is kind of increasing, it's going to, of course, have more collisions with that mercury, causing that mercury in the column to rise, and we measure that in millimeters of mercury. And the 760 is what we kind of considered standard conditions, and we'll talk about that more in a little bit. And then, of course, we have the barometer, which I think most people are familiar with. Again, it's still kind of measuring that height difference, whether you use mercury or some other maybe non-volatile or sealed off liquid that then can rise based on an increase in pressure. And you can definitely use other gases and measure gas pressure using that. So with that said, we have different units of gas pressure. And those units, and I actually have these started for you written out on what I'm going to refer to as sort of our gas law cheat sheet. Okay, and that gas law cheat sheet looks like this here. Let me close that up there. And I have a copy of this on Moodle, but it really does kind of outline all of the parts of our gas laws that we're going to be using. So we're starting off here with pressure. And the different pressure units we're going to work with are an atmosphere. So we have, that 1 atmosphere, and this is what we say is a pressure unit, is equal to another pressure unit known as a torr. So that's 1 atmosphere is equal to 760 torr. And then we have that millimeters of mercury. So like I had here shown on that manometer, standard conditions is that 760 millimeters of mercury. So that's what is equal to 1 atmosphere. So that's what we have for that pressure unit. And you notice that the torr and the millimeter of mercury are the same unit. And that's partly because, or mainly because we named the millimeters of mercury after a scientist that worked with pressure. And then our next pressure unit is a kilopascal, and that's 1 atmosphere is equal to 101.3 kilopascal. And then we have not one necessarily that we use a lot in lab, but one that I think most people are familiar with, and that's the PSI, which is pounds per square inch. Like you would put pressure into a bike tire or a car tire. So I think you're more connected to that one. So we'll work with that one. So let me just kind of move these over, and let's look at doing some pressure conversion calculations. So I'll look down here, down at the bottom of the page, and do this example, okay, on the bottom of page 212. And the example is doing a pressure conversion of the pressure inside a soda can, and we have this pressure of 4,566 torr. We want to convert that to atmospheres, to millimeters of mercury, to kilopascal, and then as you see on your page, there's also the PSI. So we're going to look at doing these pressure conversions. So let's get started with doing the atmosphere conversion. Well, of course, we're going to need that gas law unit conversion, and that is 1 atmosphere is equal to the 760 torr. So we're going to use this to do that conversion. Okay, to get started, I'm going to take my 4,560 torr, and because 1 atmosphere is equal to 760, I'm going to set the problem up like this, and that allows my units to cancel, and then I get the pressure conversion to be 6 atmospheres. So my units cancel, and I have 6 atmospheres. So this would be 6 atmospheres of pressure. Okay, the next conversion, torr to millimeters of mercury. Well, if you see, the torr and millimeter of mercury are the same unit, so we can just simply say that's 4,560 millimeters of mercury. And then to the next one, which is the kilopascal. Well, our kilopascal unit is written right here in our gas law sheet. 1 atmosphere is equal to 101.3 kilopascals. So I'm going to start with the 6 atmospheres, and to set that up, I would be multiplying by the 101.3 kilopascal over 1 atmosphere. And that allows my units to cancel. So I'm just using that pressure conversion to do this calculation. And I end up with, based on significant figures, 608 atmospheres. And then the last conversion is to go to PSI. Well, because 1 atmosphere is equal to 14.7 PSI, I'll start with my 6 atmospheres again, and then I would be multiplying by the 14.7 PSI over the 1 atmosphere, and that will allow again my units to cancel, and I'll be left with an 88.2 PSI unit. And if you think about this, again, this being a can of pop, and the pressure 456 torr, that's 88.2 PSI, which is probably about over twice the pressure that's in your car tire. So that's a pretty high pressure there in the can of pop. Okay, so we're going to do the next unit conversions of volume and temperature. So now we're going to look at volume. And volume in gas laws, as we have here on the gas law sheet, we'll be working with mainly 3 units. We're going to be working with the liter, the milliliter, and the centimeter cubed. So here's just some reminders of the units that we worked with before when we did volume conversions. So just really simply, if we wanted to say, and I'll kind of write out a problem here just to do a simple example calculation. Let's say we want to do a volume conversion of, let's say this balloon's really huge and it has 265.3 milliliters, and we want to know what that equivalence is in liters. So simply we could either do, our stair-step method and just move our decimal 3 positions to the left, or see the setup. If we have 265.3 milliliters and 1 liter is equal to 1,000 milliliters, we simply would be dividing by 1,000, so that would be 0.265 liters. So that would be our milliliter to liter conversion. And of course, if it's 265.3 milliliters, it's 265.3 centimeters cubed, because a milliliter and the centimeter cubed unit is the same unit. And in terms of gases, when we're looking at gases, so what we're seeing with gases is really just the container that we're putting the gas into. So if we make it a large container, the gases have more volume, and that volume measurement would be the size of the container that we're putting that gas in. So gases will fill the size of its container, they just spread out. So if we make the container smaller, the gases of course will contain a smaller volume. So when we measure volume, we're just really measuring the container that we put the gas into. And now we're going to look at temperature. And temperature, of course, is the measurement of the kinetic energy of the gases. So really how those gases are in motion. The quicker they move, the faster they move, the higher the kinetic energy, and of course the higher the temperature. So when we're measuring that temperature, we're measuring that kinetic energy of the gases. And the slower the gases move, the lower the temperature, the lower the kinetic energy. So with that, we have temperature conversions. And one important thing to note with gases is that we are going to work primarily with a temperature known as a Kelvin. A Kelvin temperature will be the most important temperature unit that we use with gases. Why is that? Well, Kelvin allows us never to have absolute zero. So in my modeling, if we bring the temperature down to the lowest temperature, which is that absolute zero, if you remember we talked about this back in unit 2, our absolute zero, that's when we are at 0 Kelvin. It's the lowest temperature that material would be at. So motion really does stop of the atoms and molecules at 0 Kelvin, which of course is negative 273.15 degrees Celsius. That's why we have this Kelvin conversion of taking our degrees Celsius, adding it to 273.15, so we'll never have a negative Kelvin temperature. We also have the Fahrenheit conversion and a Celsius conversion, and I have those on our cheat sheet, but if we wanted to rearrange that Fahrenheit temperature, we could have this, where we take our degree Fahrenheit, we subtract it from 32, and we divide it by 1.8, and that will then calculate our degrees Celsius. So as I have on the pages here in the book, one of the examples that we're going to look at involve doing a temperature conversion, and we're going to start with a temperature of 55 degrees Fahrenheit. And what we want to find is that degree Celsius and the degree Kelvin from this value. Well, what we would do then is we would plug that 55 into this formula right there. So I would set this up so that I have my degrees Celsius is equal to 55 minus 32 divided by 1.8, and this calculates out to be 13 degrees Celsius. And I'm going to carry it only to the ones place value because my measured 55 is at the ones place value. Then to do a simple conversion to Kelvin, it would be taking that degrees Celsius, adding it to 273.15. So I'll plug that 13 degrees in with the 273.15. I'm not going to carry it out to the 0.15. I'm just going to record it as 286 Kelvin, being that I want to keep it at the ones place value. So that's how we measure the temperature and do temperature calculations. Okay, so now we're going to talk about the last relationship that we're going to put into our gas laws for now, and that is moles. And in gas laws, the symbol for moles we're going to see is N. That's going to stand for moles in our gas laws. To talk about N, though, there's an important measurement that I need to bring to your attention, because this is an important relationship that brings moles in to some of our gas law conversions, and that's something called STP, which is standard temperature and pressure. And at STP, the temperature, our temperature is at 0 degrees Celsius, or of course that's 273.15 Kelvin. So that's the condition of STP. And then also the pressure for STP is 1 atmosphere, which also could be 760 torr, 760 millimeters of mercury, 101.3 kilopascal. At this condition, and of course, moles is the amount of atoms or the amount of molecules of the gas that you have in the container that you're studying. So if you add more atoms, if you add more molecules of the gas, you have more moles. But what's interesting about this condition of STP is that 1 mole of any gas at STP, so it has to be at the conditions of STP, occupy a volume of 22.4 liters. And that's going to be really key with doing some of our conversions. So 1 mole of any gas, and again it has to be at STP, occupies a volume of 22.4 liters. I like this relationship because what it allows me to do is it gives me the ability to measure volume and then know the quantity of moles and then further grams of the gas that I'm working with. So let's look at an example calculation of this. And the example calculation I have here is 456, and we're looking at nitrogen dioxide, so NO2, so 456 grams of nitrogen dioxide, and we want to figure out its volume. So we want to calculate volume. Well, if I have and it's at STP, right? So we have this relationship of STP where 1 mole is equal to 22.4 liters. So if I have that relationship, then what I can do is first do a calculation of my gas from grams to moles, and then I can do a mole to liter calculation. So I'm gonna do that. So first I'll take my 45.6 grams of NO2, and from the periodic table I know that my molar mass of NO2 is 46, and so I'm going to take that relationship and calculate moles. This is something we've been doing quite a few class periods so far. So we've been doing a gram to mole conversion using the molar mass. So this comes from the periodic table, that 46. And this calculation gives me 0.991 moles, which is not 1 based on significant figures, but it's pretty close to 1. So hopefully you're going to see when I take this 0.991 mole quantity and use the relationship that 1 mole is equal to 22.4 liters. I'm going to multiply that by 22.4 liters per 1 mole. Okay, it should be close to 22.4, maybe a little bit less because it's not exactly 1 mole, and it calculates out to be 22.2 liters, and that is of our NO2 gas. So that would be doing a gram to liter conversion, and the new element here is that 1 mole at STP of any gas occupies a volume of 22.4 liters. So let's put this to application with trying a few example problems here with the in-class practice problems. And I will be using the gas law sheet as my guide because I'm learning this for the first time here with you, and or you are, but I just want to kind of put myself into your place and look at that. I'll use my pressure conversions, I'll use my volume conversions, I'll use my temperature conversions. I'll remind myself of what STP is and the fact that 1 mole of any gas occupies a volume of 22.4 liters. So with that, I'm going to do some conversions of these relationships. So starting off with the first example, or the first question, where I have to convert 744 torr to atmospheres. So what I'm going to do is take my 744, and seeing that I have to go from torr to atmospheres, I'll write 1 atmosphere over 760 torr, or just simply I'm dividing by 760 torr. And I get the 0.979 atmospheres. And then what I would do with that, because the question it asks for both atmospheres and kilopascal, I'm going to do a second conversion where I'm going to take that 0.797 atmospheres and now multiply it by 101.3 kilopascal over 1 atmosphere. So I'm now multiplying by the conversion factor, and I get 99.2 kilopascal. Okay, so hopefully you're trying it, and you can pause the video and then check the answer in the setup. Okay, the next one is going from atmospheres to torr. So I'm going to take the given 1.25 atmospheres, and to convert that to torr, I would go 760 torr over 1 atmosphere, and that lets my atmosphere unit cancel, and I would just simply take my 1.25 times 760, and that gives me 950, but I'm going to put a decimal after the 0 to keep that 3 significant figures, and that would be torr. Okay, so the next one is a temperature conversion, and it's from Fahrenheit to Kelvin. So what I want to do first is get that Fahrenheit into degrees Celsius. So I will do that by taking the formula degrees Celsius, and I'm going to take my 20.5, subtract it from 32, divide it by 1.8, because I'm using my temperature conversion, degree Fahrenheit minus 32 divided by 1.8, and then that will give me a negative temperature, which is fine with Celsius. Celsius can be a negative temperature of negative 6.4 degrees Celsius. So that's just degrees Celsius right there. And then to find Kelvin, I would take that negative 6.4, add that to 273.15, takes it out from being a negative, and I'm going to carry it to 1 after the decimal based on my given 20.5 measurement, and I get 266.8 Kelvin. So hopefully that worked out for you, but you can see how I set that up. Okay, the next one involves a simple conversion of milliliters to liters. Well, if I do it in the conversion factor setup, let me make sure I write that milliliters, okay? So I have milliliters, and I know that 1 liter over 1,000 milliliters would be the conversion, or simply like we did back in Unit 1 or Unit 2, where we just kind of do the swoop, right? Those 3 positions to the left, and that would give us the answer of a 0.357 liters, from milliliters to liters. And just FYI, if I wanted to say, well, that's also centimeters cubed. Okay. So then in the last calculation that we're going to look at, how many liters are in 1.125 grams of carbon dioxide at STP? So that's important. We're looking at a condition of STP. So we have 1.125 grams. So I'm starting off with my 1.125 grams, and carbon dioxide, of course, is CO2. And what I want to do first is convert that to moles. So I'm going to use the molar mass of carbon dioxide So the molar mass of carbon dioxide is the 44, so 44.01 grams. Again, that comes from the periodic table, adding up atomic masses of carbon and oxygen. And when I calculate this, my grams are going to cancel, and I get the small mole value, because I have a small gram value, of 0.02556, and that will be moles. Then I will take that value and use the relationship of what we have at STP with a mole in a liter. So I'll take the 0.02556 mole and multiply this by 22.4 liters, and this will give me then my liter quantity, which should calculate out to be about 5727, 0.52 or 5727. And that, of course, is liters. So that's just a gram to liter conversion. So I use the molar mass to find moles, and then the moles to liter conversion of 22.4 at STP. So those are good problems to look at. I'd recommend then looking at practice problems also in the after class and doing these conversions. And you should be then all set to do some gas laws.